So today I will talk about something completely different, not network archaeology, but high-dimensional mean estimation. And I will mention several papers in this talk. Most of them are with Shahar Mendelssohn, who is at Warwick now. Yeah. So, so what is the mean estimation problem? This is the simplest problem that you can imagine. In statistics, we have n independent, identically distributed. Let me try to get rid of this. How do I do that? Yeah. So we have n independent, identically distributed observations of a. In the first half of the talk, I will just talk about the one-dimensional case. That's just a warm-up, and then the meat of the talk is in the second half when these xi's will be vector valued. Okay, but first let's just consider real-valued random variables, and we assume that the expectation exists, and we want to estimate that expected value. Now, an estimator in this talk is just a measurable function of the data. Okay, this is in contrast with a big chunk of the literature in theoretical computer science when they want efficiently computable functions. Okay, but here I just allow arbitrary functions of the data, and of course the first estimator that comes to mind is the empirical mean. And the empirical mean, well, we know everything about the empirical mean. We know the law of large numbers that guarantees that eventually the estimator will get close to the true mean. Of course, the rate of convergence can be arbitrarily slow if we don't assume anything else about the distribution but the existence of the expectation. And moreover, if we don't assume anything about the distribution apart from the existence of the expectation, then this is true for any estimator. So for any estimator you give me, I can find a distribution with finite expectations such that your estimator will converge arbitrarily slowly. Okay, so if we want to say something meaningful about mean estimation, we better assume something a little bit more than the existence of the expected value. Okay, so what is reasonable to assume? I don't want to assume too much because otherwise this talk wouldn't be interesting. So let's assume that the variance exists. Okay, that's not a too stringent condition, right? This allows pretty heavy tails. As soon as the second moment exists, we know that the empirical mean has this really nice expression for the mean squared error. This is what we teach for in kindergarten, and this is the best you can do if you care about the mean squared error. It equals d over n, and even if you know that the distribution is Gaussian, which is as nice as it gets, we cannot do better than this. Okay, and this is a classical result about sufficient statistics. Okay, but there are good reasons of not caring about the mean squared error, but something more refined. And in this talk, this is the focus that we want estimates that work not just in expectation but with high probability. Okay, and then the situation complicates very quickly. So this is in machine learning, this is called the PAC kind of formulation of the problem, probably approximately correct. So what we want is that if we are given a confidence level, delta, that's just the probability of error that we allow, what is the smallest accuracy, epsilon, that one can achieve, that holds with probability 1 minus delta. Okay, so this is the question we are interested in. And then if you take the empirical error, then it's still from kindergarten we know that that we can take epsilon to be sigma over square root of n times delta. Okay, this is just what Chebyshev's inequality gives us. okay, which is nice. So some important features here is that the scales with sigma, which is the standard deviation, scales as 1 over square root of n, and scales with 1 over a square root of delta, and that is not so good. And it's not so good because if you look at the central limit theorem, then we see that asymptotically, the sigma and the square root, 1 over square root of n are there, but the dependence on delta suggested by the central limit theorem is not 1 over root delta, but something exponentially better. It's a square root of log 1 over delta. Okay. But this central limit theorem, of course, is inherently asymptotic. So we would like to have non-asymptotic inequalities of this form. Okay. So I will say that an estimator is this is what I will call a sub-Gaussian inequality. Okay? So, for example, if we assume much more than the second moment, if we assume that the distribution is sub-Gaussian, in the sense that the moment generating function is bounded by the moment generating function of a corresponding Gaussian random variable, then by just the churn of bounds, Markov's inequality, we have that with probability 1 minus delta. The error is bounded by sigma over root n, and upstairs we have the right dependence on delta. Okay. So this is what I will call a sub-Gaussian inequality. Okay. But of course, this assumption that the tails, the moment generating function being bounded by the moment generating function of a Gaussian, this is a really strong assumption. Right? So this implies that the tails should decrease at least as fast as the tails of a Gaussian distribution, and that I don't want to allow that. Okay. All right. So the question is, can we do better? Okay. So this is just a very simple remark. That why is this dependence on delta so important? Well, it becomes very important if instead of just one mean, we want to estimate many means at the same time. Okay? And of course, and today in data science and in machine learning, we want to estimate not one but millions of means at the same time. And then if you use the union bound, then this delta gets divided by this capital M, and now you see the effect, right? If M is 100 million, then the first bound is garbage. The second bound is still meaningful because of the logarithmic dependence. Okay, so this is the main motivation of why we care about these high probability bounds with the right dependence on the confidence parameter delta, on the probability of error delta, and why we don't like what we get from Chebyshev's inequality. Okay. All right. So the question is, oh yeah. So this is. It's easy to see that if you insist on using the empirical mean, then Chebyshev's inequality is the best you can hope for. So in fact, there's no. It's easy to construct for every delta. I can give you a distribution such that the empirical mean has at least this type of error. Okay, and. It was a big surprise to me maybe 8 years ago when I started to work on this, and this was, first I saw this in a paper by Olivier Catonnet, that in fact there exist mean estimators, which are of course not the empirical mean, but more clever ones that satisfy the sub-Gaussian bounds, no matter what the distribution is, as long as the variance exists. Okay, so let me show you a couple of, and this had been known for a long time, but somehow I don't think it was in the public conscious. So one of these estimators is the median of means estimator, and it dates back to at least Nemirovsky and Yudin. People say that it's in that book, and people also say that it's in Lucien's thesis. Lucien is not so sure about it. Okay, so there are these the same kind of idea appears in several contexts. These were just clever people coming up with this simple clever idea, which is simply let's divide the data into blocks independently, and k blocks, each of size m, so k times m equals n. Compute the empirical mean in each block and take the median of that. Okay? And the surprise is that this is, if we choose the block size correctly to be log 1 over delta, I'm just going to ignore constants in this talk, then this has a sub-Gaussian upper bound. The proof is this. It's really simple. This is you can give it in as an exercise in your statistics class. So for each mean, each of the block means, we can use Chebyshev's inequality, and that will be correct with probability 75%, and it will be within sigma times square root of, let's say, 4 over m, where m is the sample size in each block. Okay, so each of these blue dots are the block means. Okay, and they are independent random variables. And each one of them is with probability 75%, is within this right window. Okay? Now, for the median of them, for the middle guy to be far away from the true mean, this is the median here, that's the true mean. In order for this to be far, it has to be that at least half of the points are far away from, are outside of this interval. Okay? But now this is just a binomial, right? The number of guys that are outside is just a binomial with success probability of at least 75%. So what's the probability success probability 75%? What's the probability that at least half of them fail? This is exponentially small in k. K is log 1 over delta, so this is how the delta comes in. Okay? So that's the proof of this really simple, nice idea. Okay, so notice that the estimator depends on delta. Okay, so this if you want an estimator that works with probability 99%, I can give you one. But if you want an estimator that works with probability 99.99%, I have to give you a different estimator. Okay, so this is unlike the empirical mean. This estimator needs to know the confidence level in advance, and this is actually necessary. I will come back to this in a second. Okay, so the median of means actually works. The exact same estimator also works even if the variance doesn't exist. It's very easy to prove the analogous statement when just 1 plus alpha is some positive number, alpha's moment exists. Then we get this upper bound. And notice that here we don't get the 1 over square root of n rate anymore. It's a little bit worse depending on alpha. But otherwise, the dependence is logarithmic in 1 over delta. And this is optimal. There's a lower bound, you see. The only difference is the constant there. So no estimator can do better than this. Okay? And this is kind of nice. It shows that when alpha equals 1, so that means when the variance exists, then things change all of a sudden. So as soon as the variance exists, we have the sub-Gaussian 1 over square root of n rate sub-Gaussian bound. We don't gain anything by having more moments, for example, but up to that 1/2. If we don't have the second moment, then we have a slower rate of convergence. Any estimator has to have. Okay, so there's this kind of a phase transition where the second moment exists. Okay, yeah, so there's this survey paper that Shahar and I wrote a couple of years ago. You can read all these proofs there. Okay. Now, if you talk to practitioners, then they don't use median of means. Practitioners have just said, okay, if you have outliers, let you just get rid of them and take the empirical mean of the rest. Okay, so this is the trimmed mean estimator, and of course this goes way back, and there was a lot of theory about this, but it was only recently by Roberto Imbuceiro Oliveira and his student who proved that this is actually, the trimmed mean has this nice sub-Gaussian property, as long as the number of outliers, number of points that you chop off is chosen correctly. And what you have to chop off is log 1 over delta of them. Okay? So just a constant number of points we get rid of. This constant, of course, depends on delta. And then if we truncate them, take the empirical mean of the rest, then this has the sub-Gaussian property. Okay? So here's a slightly more complicated version of the estimator, but slightly easier to analyze. Let's split the data in 2 halves. Okay, so let's say now we have 2n data points. The second half of the data, the y1 to yn, I will only use them to truncate, to estimate the truncation level. Okay, so epsilon is now the fraction of the points that we truncate. So it is epsilon times n, that will be log 1 over delta. Okay? So we estimate this alpha and this epsilon and then 1 minus epsilon and quantize on the second half of the data, and now with this function phi is just I guess I can draw pictures. It's just this clipping function that clips the identity at the level alpha and at the level beta. Okay, and so everything that's greater than beta will be brought back to beta. Everything that's smaller than alpha will be pulled up to alpha, and then we take the empirical average of that. I guess the picture is here. Okay, so the red points are the y points. Here we take the third point from the left, the third point from the right. Those are the quantiles, the empirical quantiles. They determine this alpha and beta, and now we take this phi function of the green points and take the average, and that's our estimate. Okay, and then you can prove, it's really not difficult. It may be half a page to prove that that this works. This estimator also works. Okay, it has the sub-Gaussian performance. Again, the estimator needs to know delta. Okay? I'm not going to talk about adversarial contamination, but there's a big chunk of the literature that allows an eta fraction of the data to be completely arbitrary. Okay? And this is the strongest kind of contamination model, where an adversary knows what estimator I will use. It can look at the data and select an eta fraction of the data and change it arbitrarily. Okay? And so these estimators, both the trimmed mean and the median of means estimator, are also robust with respect to not only heavy tails, but also with respect to adversarial contamination, and what one can get this type of bound, so that we have that sub-Gaussian bound, but now we have an extra square root of eta appearing, and that's the best one can do. Okay?
Yes, but in this case, it's not really robust, because you have to know x. And in principle, if you want robustness, you should not know the number of outliers.
Well, you need to.
Exactly the
okay.
number of outliers.
Yeah, that's a good point. But yeah, if you know an upper bound, then that upper bound will appear here. Yeah. So if yeah, so this, of course, yeah, that's true. If the distribution has actually nicer tails, then the square root of eta can be improved to almost eta, but not quite eta. Okay, so if the distribution is sub-Gaussian, then one can get eta times square root of log 1 over eta, and that's actually the best that one can get. All right. Yeah? Yeah? But they concentrate to the they don't have to really concentrate well. Okay. It's just for the analysis to be half a page. No, that's.
So would it still hold without splitting?
Yeah, you don't have to split. The simple trimmed mean estimator also works. Okay. This is just easier to teach. That's all. And also in when we generalize estimators, then I'm showing you this version to you because we will use it later in the high dimensional setup. Yeah, but you don't need. So this is what I already mentioned before. I'm just going to go very quickly through it. You need to know delta. Okay? So if you want sub-Gaussian estimators, then it is then the knowledge. So there's no mean estimator that works for all values of delta. Okay. So we say that an estimator is a multiple delta sub-Gaussian estimator for a range of these deltas. Let's say starting from delta min all the way up to 1. If we have this sub-Gaussian performance for this single estimator that doesn't depend on delta in this whole range, okay? And then you can prove that if we know something, if the variance of the distribution is known up to a constant factor, then one can find a multiple delta estimator all the way down to exponentially small deltas, and that's the best one can hope for. But if nothing is known about the variance, then we are dead. Then there's no multiple sub-Gaussian estimator for any non-trivial value of delta. Okay, so there's a really sharp construction. So in general, the reason you need these deltas is because some knowledge of the variance is because if you have that, then you can construct confidence intervals, and then you can use kind of Lipschitz method to choose adaptively. But if you don't have confidence intervals, then we're dead. Okay? So if you know something about the distribution, which is sufficient to construct to have an estimator of the variance, it doesn't have to be a sharp estimator. All we need is just up to a constant factor correct. Then we can make this adaptive to delta. Okay. So as I said, my interest in this topic started from Catoni's paper, who introduced a very different kind of idea for constructing sub-Gaussian estimators. It was a kind of M estimators, a certain family of M estimators, and I put up here some recent work, really nice work. For example, Simo and then Stas Minsker, and also Lee and Valiant. They now get the right constant in the sub-Gaussian bound, that 2, which is what we expect from the central limit theorem. But these are much more complicated estimators, completely different ones. These two papers. All right. So somehow the main topic of this talk, that was the title, high-dimensional mean estimation. So let's move to RD. So now the problem is the same as before, but now we have vector-valued random variables, and the mean is still denoted by mu, but now it's in RD, and the second moment exists. So I assume that the covariance matrix is finite, okay? And that's the only assumption that I want to allow. The question is, can we have sub-Gaussian performance even in high dimensions? But for this, first we have to understand what sub-Gaussian performance means. Okay? So in order to understand what a reasonable goal is, we can look at what happens if the distribution is Gaussian. And for Gaussian distributions, we take the empirical mean because that's the best one can do. But then it's easy to see that we have this kind of inequality for Gaussians and the empirical mean. Okay, so if the Euclidean norm, in this talk I'm only talking about the Euclidean norm. There are papers also that extend this type of inequalities for the case when we measure distance, not necessarily in the Euclidean norm, but in some other norm. But here, let's say the Euclidean norm is the Euclidean distance between the estimator and the true mean. with probability 1 minus delta is bounded by the sum of two terms. The first term is independent of delta. It involves the trace of the covariance matrix. And the second term involves log 1 over delta, but it's only multiplied by the largest eigenvalue of the covariance matrix, the spectrum norm. Okay? So the proof is really simple because the expected value of the distance between the empirical mean and the true mean by Cauchy-Schwarz or Jensen, or whichever one you want to call it, is bounded by the square root of the trace of the covariance matrix divided by n. And then the Euclidean norm is a Lipschitz function of Gaussian random variables, so we can use the Gaussian concentration inequality, and that scales with the largest square root of the largest eigenvalue. Okay, so that's the second term just comes from the concentration of the norm. Okay, so this is our goal. I will say that an estimator is sub-Gaussian if it has this performance. I'm willing to give up that C. A problem for Simo is that can you get 2 there? Is it 2? No, can you get, I guess, 1 in the first term and square root of 2 in the second term. So, but anyways, yeah? Yeah, I agree. Yeah. So get 1 in the first term first and then think about the second term. But our C will be something like 1,000 or something. But importantly, this C shouldn't depend neither on the distribution nor on the dimension. Okay? So it's kind of an infinite dimensional inequality. In fact, everything that I will say holds in Hilbert spaces as well, as long as these quantities are finite. So if the covariance operator has a finite trace, then we don't need a finite dimension. Okay. So an obvious idea that comes to mind if you want to construct something like this is, let's try to generalize the median of means estimator. So okay, the means are easy. We can take blocks of the data as before, take the empirical mean of each one of them, and then. But now, what's the median in high dimensions? Well, there are many notions of a median. You can take a coordinate-wise median, right? You can take the geometric median. You can take the smallest ball containing the center of the smallest ball containing at least half of the data points. There are many the Tukey median. There are many notions of multivariate medians. So which one is suitable for our purposes? Actually, none of these. So if you do the coordinate-wise median, then you can use the union bound over the d coordinates, so we get an extra log d in there. And what's worse is that the trace is multiplied by that log 1 over delta factors. And that log 1 over delta factor in our requirement should only be multiplied by the largest eigenvalue. So this is not quite. If we, you can take the smallest ball median. I only put it here because this is very easy to prove. But let's say something more reasonable is to take the geometric median. So the geometric median is just the point that minimizes the sum of the Euclidean distances. Okay. And then a nice thing about this notion of the median is that it can be efficiently computed. It's a convex optimization problem, and people in computational geometry worked a lot on this. So basically, in essentially linear time, one can compute this now. And Stas-Minsker actually proved that we have this nice infinite dimensional inequality. So again, this is almost like what we want, but not quite, because the trace appears multiplied by log 1 over delta, and that's not what we want. Okay, but in practice, I think this is a very good thing to try. And in fact, one can show that this type of median of means estimator with this median cannot is not truly sub-Gaussian. So you actually do need the trace in front of the log 1 over delta. Okay? So a few years ago, we managed to construct an estimator that is truly sub-Gaussian in the sense that I said, and we call this the median of means tournament estimator. So let me describe this. So the mean is, we can think about the mean as the minimizer of that function f of x, right? Which is just the expected square distance of x to x to a random vector. And then our tournament will say that let's take two candidate means, right? Every point in RD is now a candidate, and now we can try to use the median of means estimator to decide which one is better. Okay? So for which of these points is f of x smaller? Okay. So this tournament, and now we can run a tournament over all points of RD. Okay? So this tournament ideas go way back, and I think Lucien can confirm that it's in his thesis. 83. Okay, sorry. So here's the estimator. Again we take blocks. We divide our data into blocks of size m. So there are k of them, and we take the average, the empirical average within each blocks. These are the y sub j's, and from now on we just work with these k points. And then we say that A is better than B if A is closer to more points than B. Okay? To at least k half of the points. Okay? Here's a picture. So here in this picture, I managed to come up with an example of 11 points where A defeats B, B defeats C, and C defeats A. Okay, you can run this tournament. So you can see if you look at A and B, then there are 6 points closer to A and only 5 points closer to B. So that means that A is better, right? It's closer to more points than B. And similarly, B is better than C, and C is better than A. Okay, so you can for every point in RD, we can look at the set of all points that defeat that point. Okay? All right. And now we just choose the point for which this set is smallest. Okay? I think this is really very similar to Lucien's ideas. So we just choose the points that are for which all the others that defeat A so the set of points that defeat A is smallest, and smallest is defined in terms of the radius. Okay, so the radius of a set is just the largest distance from A in that set. Okay, these sets are not convex; they are not nice sets, but the radius is well defined. They're all this set is always a bounded set. Okay, so this is well defined. Okay, so that's our estimator, and we could prove that this estimator is indeed sub-Gaussian in that sense. Of course, the computation is not in polynomial time, but this is really just a measurable function of the data. It's not even the way I defined it. We have to go through all points in RD. You can easily come up with exponential time algorithms that actually work, but very smart people in theoretical computer science actually could modify this estimator. Sam Hopkins was the first one who came up with a semi-definite relaxation of this estimator, and that he could prove that it's sub-Gaussian and it works in polynomial time, and that's the d times the number of blocks to the power of 8 is what he got, I believe. But then even smarter people came along, like Peter, and then and they could improve on this dependence. I think now the best is something like n times d plus dk squared. Is that right? something like that. So now these are getting, and then Guillaume and Jules Depersin, they also have a very, very fast algorithm that computes this. Okay. So things are looking good. Let me also show you a different multivariate mean estimator. This is based on generalizing the trimmed mean. That's also sub-Gaussian. So we again divide the data into two blocks, just as before. And the second half, we only use it to estimate the quantiles in each direction. Okay. So now what we do is I think it's better to. I have a picture on the next slide, but I think it's easier to. So we look in a direction v. So v is just a unit vector here, and now we project every point on this direction, and now we have a one-dimensional problem. And in this one-dimensional problem, we compute the trimmed mean. Okay? Exactly the same way as I defined before, well, by splitting the data and so on. Okay? And so now we know we have in this direction we have this point as an estimator, and now and we do this in all directions. Okay? So in this direction this will be my estimator. In this direction this will be my estimator. Okay? So okay, but now so that's this is this u sub q of v. That's this one-dimensional estimator here. Okay. All right. So notice that here we widen this the range of between alpha. Remember, alpha was this epsilon n quantile, and beta is the 1 minus epsilon quantile in this direction. But we widen it a little bit by a number q, which is a parameter, which we will choose at the end. Okay. So for each q, we can compute the trim mean estimator with this little bit widened quantile ranges, and then we can define these slabs. So now what I know is that the true mean in this one dimension should be close to this. So that gives me that the true mean should be somewhere in this. We call this slab. Okay, and now we do this in all directions. Okay, we have these slabs. Okay, and we just take the intersection of all these slabs. So that's a convex set, right? It's an intersection of these convex sets, and so that is for a given q. And now we compute this for all q's discretized on this dyadic scale, and we choose the smallest possible value of q such that the intersection of these slabs is not empty. Okay, that's the estimate. Right. So for each q appears twice, right? Q appears here in the index. When this is how we widen these slabs, and also q appears here. Okay, which is the width. All right. So we take the smallest q such that this thing is still not empty. And the reason this works is okay. So here's the picture, but it's the same picture as there. I don't know if you can get anything out of it.
Do you really need to take all directions, not restrict to a small number of directions?
You can discretize, but you need exponentially many directions. Yeah, you could discretize. Yeah, we don't have a computationally efficient version of this estimator. And then the main technical result to prove that this works was to show that for an appropriately chosen value of q, mu, the true mean, is contained in this intersection with probability at least 1 minus delta, and that suffices to prove. Yes?
You can
Dependence on the dimension.
Yeah, how you avoid it.
How we avoided it? Well, it's because of this fact. Yeah. It's not a simple unit. No. Yeah. Well, we need so in order to prove this, we need a proper empirical process inequalities that scale with the right. Okay. So this was all this was the introduction, and now in 10 minutes I will show you the results that are newer. So. So the sub-Gaussian inequalities were for the Euclidean distance between mu and the estimator. Okay, and what we proved is that with probability 1 minus delta, the Euclidean distance is bounded by the sum of these two terms. Right, one of them is scales with the spectral norm lambda 1 times log 1 over delta over n, and the other one with the trace, which is the sum of the eigenvalues. Okay, and but equivalently, we can write that in each direction, if we project in that direction, then the distance is at most that quantity. Okay? But if I write the inequality in this form, then you may wonder whether we can improve it by putting something that depends on the direction on the right-hand side. Okay? In particular, if we fix any direction, then it should morally scale with the variance in that direction, right? Not with the worst. Lambda 1 is the worst variance in any of the directions. Okay? So wouldn't it be nice to have something where this lambda 1 here is replaced by sigma squared of u, so the variance in that direction. Okay? So the question is, can one guarantee something like this in all directions or almost all directions, and what's the price that we have to pay for it? Okay, so if we could improve this lambda 1 to sigma squared of u, what do we have to put here so that we have this inequality? Okay, so that's the question. Here's a motivating picture. So right now what we can show is that the estimator that all these estimators are within a certain distance of mu, so that means that we are in here. But now it would be nicer if we could say something which scales with the variance correctly in each direction, right? Because in high dimension we don't have this nice spherical data usually. Okay? So can we have this? We call this direction dependent accuracy. Okay, so this is just a small remark to say that we do need a global term. So we cannot hope we cannot hope to get just this. We have to have something global here, because you can just think about isotropic Gaussian. Right? In that case, the best you can do is, this is easy to see, is square root of d over n plus log 1 over delta over n, right? The variance is just 1 in all directions, right? So here we have the right thing, but there's the square root of d over n which is inevitable. So that's somehow a global penalty that we have to get in order to guarantee that things hold in all directions. Okay? So so what is the best achievable global penalty? Okay? If we want the second term to scale with the variance. So again, we can see what happens with Gaussians. Okay, so if we have a multivariate Gaussian distribution with mean mu and covariance matrix sigma, and we take the empirical mean, again that's the gold standard for Gaussians. And now we can ask the question: suppose that we have an estimator that has a guarantee in each direction that scales with a square root of the right direction of variance over n times log 1 over delta plus a global penalty term. Okay? And this is true for some value of c. Then what's the smallest s that one can hope for? Okay? And for Gaussians, it's easy to see, well, easy, it may be a one-page thing to see that the global term s has to be at least some constant. This constant c prime depends on the c that I give you here, on this c guarantee here. Some constant times the square root of the sum of the eigenvalues divided by n. But interestingly, this sum is only starting at log 1 over delta. Some constant times log 1 over delta. Okay? So actually, we don't even need the whole trace here, just the contribution of somehow the smaller eigenvalues. Okay? And moreover, so this is a lower bound, but actually this is achieved by the empirical mean. Okay? So that's the right. There's no contradiction here because you see, if we replace the sigma squared by lambda 1, then that will be as large as the sum of the lambda 1 times log 1 over delta. That's larger than the thing that we chop off here from the trace, right? Because we chop off log 1 over delta, log 1 over delta bigger eigenvalues. Okay, so we can in fact hope to decrease the global term, at least for Gaussians. That seems to be the case. That we can, by making this inequality direction dependent, even the global term decreases. Okay. All right. So the main result is that this is possible to do for all distributions under some conditions. So I guess I shouldn't have said for all distributions. So it is true for a large class of distributions. Okay? And we don't know how to do this under the only condition of second moment. We need a little bit more. So what we need is that some higher order moments exist. Okay? And this q can be anything. It could be 3, but it could be 2.1. Okay, or 2.01. So if we have a value of q such that in each direction the qth moment is bounded by the second moment uniformly. So this kappa is just a number. Okay, this cannot depend on the dimension. This cannot depend on anything. So if we have this uniform control over a little bit higher moment than the second, then we can construct an estimator that will depend on these values, kappa and q. So the estimator needs to know this condition. That has the right form, where this constant c again depends on kappa and q. Okay. So as kappa goes to 1 and q goes to 2, this constant explodes. But if q is 3 and kappa is 10, then it's just a number. Okay. All right, so one can have this direction-dependent accuracy that looks exactly as the best one can hope for even for Gaussian distributions, as long as we have such a condition. Okay, so this condition is satisfied. Of course, it satisfies for Gaussians. It's satisfied for log concave distributions. It's yes.
Based on the directional bound.
Yeah. That's just lambda 1 here. Yeah.
So the left-hand side and
That's so if you take the max on both sides, then you get the previous one. Yeah. Yes.
there's no dimension.
There's no dimension. No. This is sub-Gaussian. The only caveat is that we don't have this for all distributions. No, this is true uniform. This is true for all. So with probability 1 minus delta, in every direction we have that. Yeah. If you just have one, if you're interested in just in one direction, then you don't need this strong term at all. Yeah. Okay. Yeah. constant. So this global constant now here depends on Q and kappa, so it's not really a constant. So before we had...
No, I mean the second term.
The second term is a little bit smaller than what we had before.
Now I get also
But not really, because the first term, whatever we gained here is now eaten by the lambda 1 times log 1 over delta, if you take the supremum. So there's no improvement there. Exactly. Okay. So, okay, just really quickly, how the estimator works. It's a version of the trimmed mean estimator. First, we have to do a little bit of smoothing. So we have to take blocks. Now, these are of constant size. This m depends on kappa and q. And the reason we do this is because we need, this induces some small ball conditions that we need. Okay? So we take these little blocks, a bit of smoothing, and then we do this kind of trimmed mean estimator on these blocks. Okay, but now the slabs are defined not as before, but now in each direction we have to estimate the variances. And this is why we need this extra condition. Okay? And the variances need to be estimated up to a constant factor. They don't have to be very, very good. It's enough if we are, let's say, within a factor of 4. And also, we don't need it in all directions, just the directions where the variance is not too small. Okay? And again, one can construct such an estimator using kind of trimmed mean ideas that work, yeah, like that. And then we do these slabs, and we take the intersection again. Okay, so I will skip all of everything about the proof. And this is just some questions to you guys. So, is it possible to have a direction-dependent accuracy, this sub-Gaussian direction-dependent accuracy for all distributions of finite second moment? I think that's a really nice question. I have no idea, because I mean, if there is one, then it requires completely new ideas, because our estimator really needs to have at least some kind of a guess of how what the direction of variances are. Making the estimator adaptive for Q and kappa, that's probably a little bit easier problem. And a really hard question again is there a computationally efficient version of this, which I have no idea about. Okay, and these are the references. Okay, thank you.